welcome everyone. Today we are going to present about a research paper which is Tunnel FETs for ultra low voltage digital VLSI circuits. This is the part 1 of the device circuit interaction and evaluation at device level. So let's get into the topic. So first we will give a brief introduction about the paper, what are the objectives and what is the basic things that you need to know about before going into the topics. Then we will one by one get into the depth that what this paper discusses about and what they tell about. So first of all, let's understand what is the objective of this paper. So the objective of the paper is it presents a comparative study about the conventional MOSFETs and TFETs for ultra low power application, because these days ultra low power applications are very much needed for IoT applications and all other stuffs where the power considerations are top of the priority, right? So this presents a simulation and test results, analysis of them, and it gives a bit of hint about the future scope of TFET in ultra low power application. So till now you might have been wondering what is TFET. TFET stands for Tunnel Field-Effect Transistor. So the tunnel word here, it comes from its working principle, which is quantum tunneling effect. So what is quantum tunneling effect? We will get into the thing within a moment. But first, let's get into why TFET. So why TFET is because the challenges in scaling of MOSFETs for ultra low power application these days. See, with the power considerations being top of the priority nowadays, we have to somehow go beyond 500 millivolts. The application. See, VDD will have to go beyond 500 millivolts so that we can match that power considerations. And another thing is that tunnel FET shows a very good subthreshold slope, which is very lesser than the conventional MOSFETs. So they are, of course, a very good candidate for substituting MOSFETs in ultra low voltage applications. So now, what is quantum tunneling actually? Quantum tunneling is a very special kind of phenomena that happens only for quantum particles. Quantum particles means very small particles like electrons. So quantum tunneling is a thing that actually does not match with the classical physics rules. So let's understand with the analogy. Let's say you have to take this stone to the other side of the hill. So how are you going to do this? So you can take it all the way up to the hill and then you can roll it down. So for that, you have to give this stone the potential energy to reach this point, and then you can roll it down. And another thing is that you can just tunnel it through the barrier. If you consider this hill as a barrier, you can just tunnel it through the barrier. So that is quantum tunneling. So this barrier, in case of electrons, we can think it about like a voltage barrier. Okay. So even though this stone is an electron, even though this electron does not have the energy to pass this barrier or force through this barrier, still it has a chance to appear on the other side of the barrier, which is quantum tunneling, as if it passes through a tunnel. So as in this diagram, you can see the energy band diagram. From the valence band of the p type, it jumps into the conduction band of the n type material, just like a tunnel. So that's all for tunneling, quantum tunneling. Now getting to let's have a brief overview of 3 types of MOSFET that we have nowadays. So 2 types of MOSFET and TFET, a comparative analysis. So the subthreshold bulk MOSFET is the conventional MOSFET that we see at everyday applications. And then comes the SY MOSFET. SY MOSFET is also there. SY MOSFET is a special type of MOSFET which stands for silicon on insulator MOSFET. So these type of MOSFETs have one source, drain, and instead of directly adding the substrate in between the source and drain, what we do is that we put an intrinsic semiconductor layer, then we put an insulator, and then under that we put a substrate. So what this structure does is that it removes a lot of parasitics and gives us better characteristics in terms of operation. And then comes the tunnel FET. So tunnel FET is a very special kind of device where you can see source and drain. Both terminals are doped with different elements. Like one is doped with the n-type element, another is doped with the p-type element, and the channel is intrinsic type of channel, intrinsic material. And then the subthreshold slope, as I told earlier, the subthreshold slope of the bulk MOSFET is around 60 millivolt per decade. Same for SY MOSFET, because this is the inherent characteristics of the MOSFET, like the device itself. You cannot reduce less than that. But the tunnel FETs, what they show is that they show less than 60 millivolt per decade slope. Same for the scaling limits. See, bulk MOSFETs are limited by SC. SC stands for short channeling effect. And then SY MOSFET, they have a better scaling, but still not that much scaling that we desire nowadays. Let's say less than 500 millivolt application for. So they have better scaling because they have suppressed short channeling effect. And then the tunnel FETs, they have excellent potential for scaling down. Power consumption. Bulk MOSFETs consume a lot of power, so we invented the SY MOSFET, which consumes a lower power. Then we have to go to the ultra low power application where SY MOSFET also fails. So there, the tunnel FETs have a chance. And speed and drive. See, bulk MOSFETs have a lot of current carrying capacity. So of course their speed and drive are very high. Similarly for SY MOSFET, they are also very high drive devices, but tunnel FETs are very low drive like devices. Then fabrication complexity. See, bulk MOSFETs are everywhere. So the fabrication technology have evolved over the decades, you can see. So the fabrication complexity has come down to a large extent. So they are very easy to fabricate. SY MOSFET has a little bit of complexity, but the tunnel FET, these are very new, and the fabrication itself is a very complex thing for tunnel FETs. And as we discussed earlier, applications. See, bulk MOSFETs are have everywhere. They have application everywhere. And then SY MOSFET, wherever we need high performance RF, like radio frequency applications, there we use SY MOSFET, silicon on insulator. And the tunnel FETs. Tunnel FETs are basically, they are directed, or let's say the aim of introducing tunnel FETs are for very low power applications where speed is not a matter of intention. The power considerations are more priority. So the IoT, biomedical application, these are the places where we can use TFETs. So now coming next, these two are the plottings of the IDS versus VGS. So get to source voltage and drain to source voltage. As you can see, the TFETs, both NFET and PTFET, NTFET and PTFET, both shows a good subthreshold slope, better subthreshold slope compared to SOI and bulk MOSFET, which is less than 60 millivolts. For NTFETs, it's 29 millivolts per decade, and for PTFETs, with 36 millivolts per decade.
Now let's look at device-circuit interaction at the ultra-low voltages. That is the section 4 of our particular research paper. So we can see that there is a graph of drain to source potential versus the VDS for NTFET, NMOS silicon on insulator, and NMOS bulk at the gate to source potential is equal to 350 millivolts. Now, the TFET shows poor linearity at low VDS, as evident in this particular section. That it shows poor linearity at the low VDS due to a tunneling threshold, and due to this tunneling threshold, what happens? IDS increases only after a certain VDS. Now, this MOSFET, if I talk about this MOSFET, this is the line indicating the MOSFET. It shows near linear rise and early saturation due to trip diffusion transport. It's one of the factors responsible for the linearity in MOSFETs. Now, TFET requires higher VDS to reach saturation, affecting gain and delay at the low VDS. That is quite evident from this particular graph. Now, let's look at the gate capacitance versus the gate to source potential. So, we can see this particular graph in which we are indicating NTFET, SOI, bulk at drain to source potential is equal to 500 millivolts and drain to source potential at 0 volts. So the TFET exhibits significantly higher gate capacitance compared to MOSFETs, as evident from this particular graph. Like we can see here. See this particular graph. This is nothing but for NTFET at 0.5 volts exhibits higher gate capacitance than the MOSFETs. Now MOSFET gate capacitance is nearly constant in the subthreshold region. We can take this to be the subthreshold region. So it's constant in the subthreshold region dominated by the parasites, because overall effect of the parasites does what? It tunes the capacitance of the MOSFET so that it doesn't vary too much. Now, TFET gate capacitance increases due to onset of inversion in the channel, and larger TFET gate capacitance increases the higher dynamic energy consumption. Why is that? Because once gate capacitance is more charge carrying capacity, and therefore higher dynamic energy consumption. Now, let's look at this particular capacitance. That is nothing but the gate to drain capacitance versus gate to source potential. Now, the gate to drain potential CGD dominates total gate capacitance in TFET. It is the dominant factor for the gate capacitance in the TFETs. This is due to early inversion at the drain side. Large Miller capacitance. Due to large Miller capacitance, what happens? More charge carrying capacity, and therefore by applying a slight amount of voltage, we can have the inversion. That's why due to early inversion at the drain side, larger Miller capacitance, we can have a flourish of charges. Now, CGD gate to drain increases sharply with VGS contributing to higher switching delay. We will see when we look at the inverter characteristics how switching delay affects. Now, highlights the importance of minimizing CGD via this device design. Next, let's look at the IDS VDS characteristics for NSRC. By tuning NSRC, that's nothing but the source doping concentration. Let's look at this. We can see WF is equal to 4.2. What is all these things? This is 4.2, 4.155, 4.10, 4.04. So it's nothing but the work functions. The work functions are adjusted so as to keep the I off to be equal to 10 picoampere per micrometer. That is nothing but the match current. Match reverse saturation current. Now, increasing source doping makes the TFET output more like output of that MOSFETs. So we can see that this is the characteristics. These are the characteristics when we are changing the source doping concentration. Let's concentrate on this region, that is the subthreshold region. We can see when we are increasing the source doping concentration, what is happening? Our IDS, drain to source current, is increasing. That is what we want. That's why it highlights the importance of tuning work functions, increasing the source doping concentration. But the source doping concentration must not be made too high, because it will then degrade the subthreshold slope, because it's going to make the make the PN to be nothing but degrade. It will degenerate the material. That's what we don't want. Next, let's move on to the next section, that is 4A, source doping optimization to increase voltage gain and reduce TFET gate capacitance. Now we can see the P-out P-in characteristics, that is the gain V-out P-in characteristics for TFET inverters. Now we can see when we're increasing the source doping concentration, our response is becoming more that of an ideal inverter. Higher in NSRC increases the inverter voltage gain significantly. Reduce linear region, that means sharper switching. Better IDS VDS strengthens gain and restores proper logic transfer curve, and demonstrate how source doping tuning improves the circuit robustness. So circuit robustness can be enhanced by source doping concentration tuning. Okay, that is what we actually intend to do. Now, let's look at the gate drain capacitance variation with respect to gate source for TFETs. Now, we are changing the source doping concentration. That means we are increasing the source doping concentration for NTFETs. And what is happening is the response. The response is shifting towards the right side, and this reduces the gate to drain capacitance in the operating region, lowering effective dynamic capacitance. Now, the CGS gate to source capacitance remains unaffected by NSRC changes. The work function adjustment requirement to keep I off to be equal to 10 picoampere per micrometer for matching. Now, let's look at the 4B section, that is leakage imbalance trade-off and threshold optimization. So we can see that there is an imbalance factor. That is nothing but for minimum size N-type and P-type transistors. This is what? Nothing but the imbalance factor. So imbalance factor we need what? Because see, we have NTFETs, we have PTFETs, they have different subthreshold slopes. We have already seen that. Also at the same time, their behavior changes with respect to certain parameters. So due to which an imbalance is being created, and that the factor responsible for bringing or highlighting this imbalance is nothing but imbalance factor. This imbalance factor quantifies the mismatch between the N and P type device strengths, and TFET shows high imbalance at VGD less than 250 millivolts, caused by weaker P TFET. Adjusting PTFET work function reduces imbalance factor, stabilizing the CMOS logic behavior. SOI and bulk MOSFETs show near constant small imbalance factor due to match subthreshold slope. That is quite evident from this particular picture. So we can see that this graph is having the TFET original work function. This is the SOI, this is the bulk, this is the TFET P channel work function increased by 20.2 millivolts, and we can see very well that the work function, the original TFET is having very high imbalance factor compared to the SOI, bulk and P TFETs, and this formula is giving the imbalance factor. Next, we have the normalized leakage versus the imbalance factor. The normalized leakage is nothing but given as the approximate is the average of the op current, the leakage current in P TFET and the leakage current in N TFET under ideal conditions. Delta WF denotes the change in the work function to work function of the P-type transistor with respect to work function is equal to 4.987 volt corresponding to I of 10 picoampere per micrometer at VDD is equal to 500 millivolts. Shows trade-off between the leakage increase and the transistor balance, because if I'm increasing the imbalance factor very high, then what happens? My leakage increases. That means there is a trade-off between the imbalance factor as well as the leakage. We cannot have betterment or optimization at both cases. We have to compromise one of the others to get the others, right? Increasing P TFET work function increases leakage but reduces imbalance. Minimum of leakage and imbalance product identifies optimal work function shift, approximately 20 millivolts. Important for achieving robust low VDD circuit operations. Now let's look at the fifth section of this research paper, drive currents and effective capacitance. Now we can see that the drive current and effective capacitance, this is the I of op current versus VDD. So this is the graph for P TFET, this is for SOI, this is original TFET. Work function is kept same, the work function is being tuned so that it is increased by 20.2 millivolts, and normally this op current is defined as the average of op current for N TFET and op current of P TFET. Okay, so we can see from this particular equation that is what is being think. So the TFET leakage nearly constant with VDD. So this TFET, original TFET, is leakage nearly constant with VDD determined by tunneling mechanism. Then MOSFET leakage decreases at lower VDD due to Dvlsi, drain-induced barrier leakage reduction. After work function tuning, P TFET leakage becomes slightly higher than MOSFETs. Leakage difference becomes critical in standby power analysis. Next, let's look at the on current versus VDD. So this is for N TFET, NSOI and NBUT. That's the behavior. TFET offers massively higher ion at low VDD at 200 millivolt. TFET ion is approximately 20 times the silicon on insulator and 200 times the bulk MOSFET. That's why we use TFETs nowadays. Very advantageous. Advantage arises from steep subthreshold slope. Strong indicator of TFET suitably for ultra low VDD digital logic. Next, we have the graph between the effective gate capacitance and the VDD, and VDS is set to VDD. So MOSFET's gate capacitance approximately constant at VDD subthreshold. So this is my MOSFET. These are my MOSFETs. This is MOSFET, but we are increasing the source doping in this direction. Am I right? We're increasing the source doping in this direction. So what happens? Higher in SRC, significantly lower effective gate capacitance, better speed or energy. TFET gate capacitance decreases with VDD as parasitic region increases, widens. SOI gate capacitance increases only above approximately 400 millivolt when inversion begins. That is quite evident from this particular section of the graph.
The first figure looks at the off-stack factor, which is defined as the ratio of leakage current of a single device to the leakage of a stack of two or more devices. That is, it tells us how much leakage drops when we place transistor in series. TFET off-stack factor is much higher than MOSFET, below 350 millivolts. This is because TFET have much higher steep sub-threshold slope. So when we stack devices, upper device experience a lower gate to source voltage. Even a small drop in VGS causes a huge reduction in tunneling probability. This reduces leakage current. In contrast, MOSFET leakage depends on thermionic emissions, which is much less sensitive to changes in VGS. The second figure shows how much on current we lose when transistors are stacked. At low supply voltages below 150 millivolts, TFET stay mostly in steep tunneling region. In this region, stacking has less impact on TFET on current, because the slope side tunneling junction still dominates. For MOSFETs, we see a significant drop in on current as VDD increases. So, this slide shows how leakage current varies with changes in equivalent oxide thickness. TFET conduction relies on band-to-band tunneling. Thinner oxide steepens the band bending and exponentially increases tunneling current. MOSFET leakage changes moderately, while TFET gives great reduction in leakage current, but they are highly sensitive to oxide thickness variations. For MOSFETs, as gate length shrinks, off-current increases significantly. This is due to short channel effects as threshold voltage decreases. For TFETs, off-current barely changes with gate length. This is because TFET leakage is generally by band alignment at source, which is unaffected by gate length. Therefore, TFET is immune to gate length variability. For on-current variations, TFET shows much less sensitivity than MOSFETs. In MOSFETs, reducing gate length affects channel resistance, mobility, and threshold. Thus, on-current vary noticeably. This means TFET are much robust to process variations. To conclude, the authors present a device-level evaluation of TFETs compared to SOI MOSFETs. For ultra-low voltage digital VLSI applications, TFETs outperform MOSFETs in deep threshold region because of the steep sub-threshold slope and band-to-band tunneling mechanisms. Therefore, below 0.3 to 0.4 volts, TFETs deliver higher on-current, lower off-current, and better stacking behavior. TFETs exhibit larger gate capacitance and require careful balancing of N and P device strengths, and their leakage is highly sensitive to process variations like oxide thickness, silicon thickness, and doping abruptness. Overall, the paper concludes that TFETs are promising devices for voltage scaling and ultra-low voltage power logic circuits. Thank you.